Okay. All right. All right. All right, so let's go ahead and get started with whatever we're going to accomplish today. So the exam is on Monday, right? In this class, same time. All you need is your pencil and your calculator. That's it. And it's going to cover chapters 1 and 2 and the simple math, right? Chapters 1 and 2 and the simple math. That's what your first exam is going to cover. All right? Any questions, concerns, or comments? So do we feel any more comfortable or less comfortable with conversions? Feel more comfortable? Good. Well, if you don't feel more comfortable, then I would suggest you get some practice. Okay? Or get some help from somewhere. All right, so how many people are looking at the e-text? Okay. So very few. All right, well, that's good. Because we're going to look at it today. All right? So, if you don't want to look at it on your own, we'll look at it together. All right. So let's check out this first video and let's see what it's about.
And what do we have down here again? We have some plates. No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university. Okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Yeah, how about that?
Okay, so that's obviously an example of the first law of inertia, right? And we went over that several times, okay? But it's always good practice to see things
Go to the store, you get
in
some
real life.
groceries at the store. You got the baggies, huh? You get the baggies all set, and you got all your bananas right here, and you're gonna get the baggie. Do you have to put all the bananas down? Put one hand on top of the baggie thing and pull the other. Do you have to do that? You don't do that. You keep the bananas in one hand, you grab the bag, and you go, you snap it. And when you snap it, what happens? The roll of bag, so much inertia, stays right there, doesn't it? And boom, it'll snap away from you. Huh? How about when you're reading your book and you're on the toilet? Right? What happens? You're on the toilet, you're reading a book like this. Do you have to stop when you're all through, put this down, hold the top of the toilet paper, and tear the bottom piece? Do you have to do that? You don't have to do that. You can keep reading the book, reach over, and snap down quick. And you rely on the inertia to hold it still. Isn't that true?
All right. So another example of inertia. Right? That's kind of related to the where we was talking about the ball, right, hanging from the string, and if I pull it down, right, then inertia is what causes it to come down, right?
So what's the force keeping it going? No force. We don't know why it keeps going. But we call that ignorance inertia. The idea? Nobody knows why it keeps going. We just know that it does. And so we call that inertia.
Of course.
Yes, sir.
I ain't gonna lie, I forgot like what inertia is. Would you like to find it real quick?
It's the force that keeps an object in motion or sitting still, right? Well, force that keeps a moving object in motion, right? And a resting object at rest, okay? So anything that has mass has inertia, okay? Right? And that's what determines how much inertia an object has. So obviously, something that's more massive has more inertia, right? And the opposite is true as well, right? So let's look at this.
This has got a lot of mass in it. To say it's got a lot of mass, to say it's got a lot of tendency to stay right where it is. Okay, I'm going to lay on here. Would you put the anvil right in my stomach, please? Right in my chest. Okay, right here. Okay. Now, as you get on the other side, slam that thing as hard as you can. Over here, Trey. Oh. Please don't miss the anvil. Do you have any grudges against your teachers? Hit it harder.
So you think that would be, yeah, hurt,
That's
right?
what I thought.
Huh?
That's what I thought would happen.
Right.
Yeah.
But because it's so massive, right? Probably more massive than the mallet, right? When it connects with the mallet, the anvil, right? It doesn't transfer very much energy, right? Or the energy it does transfer is not enough compared to the energy inside of that anvil because it's so much more massive. You following me?
Yeah.
Right? So the inertia, which keeps the anvil sitting still, right, is going to do exactly what that. Is going to do exactly that, right? Keep the anvil sitting still. or, you know, maybe it moved slightly, but not enough to hurt the guy underneath, right? All right. So let me see if we can find some more of these. Here we go. All right. Y'all gotta look at these videos.
We talk about forces. We're going to talk about forces not in terms of pounds, Candy, but in terms of newtons. Here's a Newton scale.
Not in terms of pounds.
Here's a kilogram.
That's weight.
I'm going to weigh the kilogram.
Pounds.
A kilogram
is
is a weight, gravitational pull, of almost 10 newtons. Want to get strict? 9.8. But we can say
9.8,
10
right?
newtons. So 1 kilogram
G.
weighs 10 newtons. 10 newtons of gravity force.
Right? So that's where we get the force, or the unit for force, right? Is 1 Newton, which is the force exhibited on 1 kilogram, right? Well, the force generated by gravity on 1 kilogram of mass, okay? That's 1 Newton. Okay, that's where you get the 10 meters per second squared, right? For the acceleration due to gravity.
Changes in motion are produced by a force or a combination of forces. A force, in the simplest sense, is a push or a pull. Its source may be gravitational, electrical, magnetic, or simply muscular effort. Here's a box of candy, say in free space. It's free to move. Let's suppose we exert a 5 Newton force on it. That's a bit more than 1 pound. This red arrow drawn to scale is a vector. A vector is a vectorial arrow that shows both magnitude, how much, and direction, which way. The 5 Newton force can produce a pickup in speed of the box. Suppose we exert a second identical force on the box. The pair of 5 Newton forces will double the gain in speed. But you know what? The behavior of the box would be the same whether acted on by the 5 Newton forces, both of them, or a single 10 Newton force. The box wouldn't know the difference. We say the net force of the two 5 Newton forces is 10 newtons in the same direction. The forces simply add. Suppose we pull on the box with 2 oppositely directed forces, one 10 newtons to the right and the other 5 newtons to the left. How does the box move? Here forces subtract, and it moves just as if a single 5 Newton force acts on it. The net force on the box is 5 newtons to the right. Suppose a pair of 5 Newton forces in opposite directions act on the box. What then? They cancel out. The net force on the box is 0. When the net force on something is 0, no change in motion occurs. We say the box is in mechanical equilibrium. Consider little gymnast Nellie who weighs 300 newtons, which we represent with a red vector, downward in the direction of gravity. 300 newtons is about 66 pounds. She holds onto a bar that's supported by a rope attached to the ceiling. We neglect the weight of the bar. The rope is taut under a stretching force called tension. Since she's at rest, the rope tension has got to be 300 newtons upward. So 300 newtons upward and 300 newtons downward produce a net force of how much? I hope you said 0. Nellie is in mechanical equilibrium. Suppose 3 ropes support Nellie, and evenly, so the tension in each rope is the same. We know the sum of the tensions have to add up to 300 newtons. So what's the tension in each rope? Did you say 100 newtons? If so, good. Again, Nellie is in equilibrium. Let's go for 2 ropes. Again, evenly supporting Nellie. What's the tension in each rope? Can you see it's 150 newtons? Suppose instead of attaching the left rope to the ceiling, we fix the end to a wall with this pulley arrangement.
We're not gonna, I don't think
The
we're
pulley
gonna-
simply changes the direction of the rope, not its tension. So how about tension in the right rope? It will still be 150 newtons. How about tension on the left rope? It turns out it's still 150 newtons. Interesting stuff may occur beyond the pulley, which doesn't have slanted. So the verdict learned to progress beyond that. I want to leave you with a question.
All right. Here we go.
Welcome to the first of many Hewitt-Druitt screencast lessons in physics. I'd like to tell you how my love affair with physics began after I gave up boxing and at the age of 25 began painting signs in Miami, Florida. Newly employed, I was assigned to paint with a painter who was unpopular with the other painters. His name was Burl Gray, who it turned out altered the course of my life. I remember one day when Burl was on one side of our scaffold and I was on the other side, he started twanging one of his supporting ropes. I showed just one strand of rope here for simplicity. He said, "Hewitt, twang your rope." His rope went boing, and mine went boing. He said the ropes behaved like guitar strings, and the fact that his twanged at a higher pitch was evidence that the tension in his rope was greater than the tension in my rope. That made sense because Burl was somewhat heavier than me. Tension is the force within a stretched rope. Somewhat later, I'm walking over toward Burl to borrow one of his paintbrushes, and Burl says, "Aha, as you walk closer to me, will the tension in my rope increase?" And we both agreed that it would because his rope would be supporting more of our weights. Then he asked, "As the tension in my rope increases, will the tension in your rope decrease?" It seemed reasonable that it would, but Burl went further and asked if the tension in his rope increased by 50 pounds. Would the tension in my rope decrease by 50 pounds? Or going further, if his rope increased by 50.1 pounds, would my rope decrease by 50.1 pounds? Exactly. If so, wouldn't that be wild? For how would my rope know what's happening in his rope? How would the ropes know? Neither of us had an answer to his question nor a good explanation. Neither of us had any background at all in physics. Sometimes not too quickly having answers is a good thing. Wondering can be wonderful. Discussions of this sort, and those with Burl's friend Jacques Fresco, are what prompted me to leave the sign painting profession and make a giant leap to furthering my education and learning science. Months later in prep school, preparing for college physics, I learned the equilibrium rule and shared my knowledge with Burl. The equilibrium rule states that the sum of all forces that act on a system will balance to zero if that system doesn't change its state of motion. If it's steady, for example. Burl, I, and the scaffold were part of a system, one that nicely stayed in equilibrium. The sigma sign stands for sum of. More correctly, the vector sum of all forces will equal zero for a system in mechanical equilibrium. Yum. I contacted Burl and explained the value of identifying the forces involved with our scaffold. There were 3 downward forces due to gravity. Burl's weight, the weight of the scaffold that could be considered at the center, more about center of gravity later, and my weight. If these were the only forces in the system, we'd be in free fall. But the ropes provided upward forces, tension in Burl's rope and tension in my rope. What's the sum of these forces? The equilibrium rule says that the downward forces are matched by upward forces. That the upward tension in Burl's rope plus the upward tension in my rope minus Burl's weight minus the weight of the scaffold minus my weight equals 0. Knowing that rule bypasses questions like how does one rope know how to gain and how does the other rope know how to lose? How much richer it is to know that the ropes, scaffold, and us comprise one system. And if that system's in equilibrium, then all the forces acting on it will balance out to 0. I later learned that the equilibrium rule is related to Newton's laws of motion. Learning these laws was learning the rules of nature, wonderful rules that make sense of the world. I want to leave you with a question. If Burl and I both stood at the far end of the scaffold and leaned outward a bit so the opposite rope went limp, what would be the tension in our supporting rope? Think about that. Until next time, good energy. I sign off with a short poem that I use to sign all my art. Hewitt drew it. Yum. Next time.
So, anybody got an answer to that question? Well, not this question, but you know, the one I'm talking about where both of them were on the same side. Yeah, that's correct. Yes, but they asked what would be the tension in the rope, right? Where they were both standing on the same side, and the other one went limp, right? So it would be twice as much, right? Because it would have to compensate for the tension that was lost in the other rope, right? And the fact that it's limp means there's no tension. Tension is 0, right? If the rope is limp, right? So if both of them go on one side of the scaffold and one side gets limp, then that means there's no tension here. So that means it has to be twice as much on that side. Okay? Let's see. Support force. All right, remember what the support force is? Huh? Okay, good. Let's look at friction.
I'm going to pull this block along the table. And I'm going to pull it so it has no acceleration. Let's see if I can do that. Steady, steady, steady. What was the scale rating when I pulled it? Try it again. I'm pulling against friction, isn't that true? There's friction here. It takes a lot to get started. Once I get it going, steady, steady. What was the force when it was going? About 3? 3 newtons is registered, right? Do you know there are people who could watch that and see that it's moving with no acceleration? And they know enough physics, they can say, hey, you know what? I can calculate in my head what the friction force must have been that you were moving against. And there are people that can't make those calculations. But there are people who can. And all they say is, honey, when you were pulling, it took 3 newtons to keep it going. I can tell you how much the friction was, so long as it didn't accelerate. See if you're sitting next to someone who can do such a thing in their head. Go. When I pull that, I get 3 newtons. There's 3 newtons pulling it this way. Do you guys know anyone who can calculate what the friction must be? Aren't you sitting next to someone? What's the person next to you say? How many newtons of friction? 3. How many say 3? Yay, most everybody, that's right.
All right, so do we understand what he's saying? No? He said no? Oh, okay. Anybody? All right, well, in order, it's just like what we talked about with the acceleration, right? If it's not accelerating, then that means the net force is 0. Everybody understand that? All right, so we see it moving, right? So we know it's in motion, but it's not accelerating. So then that means that the force that makes it move, there is also another force, which is what? Huh? Doing what?
What, making it slow down? No.
Making it, well, no, not making it slow down. It's canceling it. It's, if it has 0 net force, then that means, right? The force that is making it move, that means there must be another force which is doing what? In the opposite direction, which cancels it out, right? It cancels the force that he was pulling it with. He was pulling it with the scale, and so the friction force was working in the opposite direction, right? But at the same magnitude, therefore the net force is 0, so there is no acceleration, that's constant velocity, right? Remember our constant velocity problems? But A is 0. All right? Okay. Yeah, we're not doing no math today.
First definition from motion is how fast you move. That's speed. So speed, we define speed to be, speed's measured like miles per hour, so it's distance compared to time. So speed is simply distance compared to time. If I travel 60 miles and I do it in a time of 1 hour, what's my overall speed? Try it. 60 miles an hour, okay? Let's suppose I go 70 miles in 1 hour. What's my speed? 70 miles per hour. Let's suppose I go 100 miles and it takes me 2 hours. What's my speed? 100 miles per 2 hours, or 50 miles per hour, right? Can you do metric units? Let's suppose I go 60 kilometers and it takes me 1 hour. What's my speed? Yeah. What is it, gang? 60 kilometers per hour.
All right.
Ordinarily, your ratio of distance to time may change. That sometimes you might cover a lot of distance in a short time, and other times a longer distance in a longer time, so it may change. So strictly speaking, we say your average speed is how far you go divided by how long time it takes. I put that little bar there to mean average speed.
Let's skip that. Okay. This is a linear motion.
In describing motion, we're talking about what is called kinematics. That's motion without regard for force. When motion is described with forces, we're talking about dynamics. For here, we'll talk about kinematics. And in this lesson, we'll define the quantities distance, displacement, speed, velocity, and acceleration, and the relationships among them. Distance as used in physics is the same as distance in everyday language. How far something moves. It's measured in meters or some other length unit. Distance doesn't depend upon direction because it's a scalar quantity, which can be described by how much, not which direction. Here we see that Barry Biker has moved a distance d. Displacement is a little trickier. It's the straight line change in location between the starting and ending points of motion. Displacement is a vector quantity, since it involves both a distance and a direction. Consider this top view of the path that Barry Biker rides in going from location A to location B. The dotted path shows the distance traveled. The vector shows the displacement traveled, a straight line path. For motion in a straight line, that's linear motion, we won't need to distinguish between distance and displacement. For practical purposes, they're the same. In my lessons, I prefer to use distance. Speed, how fast something moves. Speed is a measure of distance divided by time. Distance per time, like miles per hour or meters per second. The equation for speed is v, we use the symbol v for speed, is equal to distance divided by time, or in shorthand notation, d over t. When we talk about average speed, we're talking about the total distance covered in a particular time interval. So average speed is total distance covered per that time interval. In shorthand notation, v bar equals d over t. The bar over the v indicates average speed. What's your average speed if you walk 100 meters in 40 seconds, for example? We see that it's 100 meters for 40 seconds. That's 2.5 meters per second. That's your average speed. We can rearrange this equation and express it for distance. D equals average speed times time. Then we see that if you walk an average speed of 2.5 meters per second for 100 seconds, the distance you travel is 250 meters. Instantaneous speed, speed at any instant. Whenever we take a trip, our speed at any instant may differ from our average speed. We likely speed up in places and slow down in others.
We're not gonna deal with instantaneous speed. All right, y'all. So, all right, so let's just go. Unit
Let's
conversion,
put
right?
some of what we've learned to use in solving a simple problem. While driving along a highway at constant speed v, fast Frida sneezes and her eyes shut for a brief time t. Write an equation for the distance Frida travels while her eyes are shut. How do you begin to solve such a problem, or most any physics problem? Well, here's how I do it. I write the d equals. That's right, I focus on what I'm asked for. In this problem, it's distance, so writing d equals gets me started.
Right.
Often the hard part.
First thing you do,
I can
right?
get distance from the basic equation v equals d over t. From v equals d over t, I rearrange it to read d equals vt. In fact, that's the solution to this problem. The equation tells us that the distance traveled while her eyes are shut is the average speed of the car multiplied by the time during which her eyes are shut. Let's put some numbers in here. Calculate the distance in meters that Frida travels during her sneeze, given that her highway speed is 100 kilometers per hour and her eyes are shut for 0.70 seconds. That's 70 hundredths of a second. Here we're asked to find the distance d in meters while speed is given in kilometers per hour. Our task is to convert 100 kilometers per hour to meters per second. We use a process called unit conversion. we set up conversion factors so that the kilometers and hours cancel, leaving us with the units meters per second. The conversion factors we need are 1 hour equals 3,600 seconds, 1 kilometer equals 1,000 meters. Conversion factors have a numerical value of 1, like 1,000 meters divided by 1 kilometer, or 1 hour divided by 3,600 seconds, each equal 1 in magnitude. So multiplying a quantity by 1 successively doesn't change the quantity, only its units. So we say 100 kilometers per hour times 1,000 meters. What do I put in the denominator? Do you see it's 1 kilometer? If so, good. Let's continue. Then we multiply it by conversion to change the unit hour to second. That's 1 hour divided by what? Do you see it's 3,600 seconds? If so, you've got it. Let's continue. Then we see it's 27.8 meters per second. That's our speed in meters per second. Our calculator tells us that the distance covered is 27.8 meters per second times 0.70 seconds equals 19.5 meters. Unit conversion is a powerful tool. Suppose our problem asked for the distance traveled in feet instead of meters. Let's suppose the conversion factor we know is that 2.54 centimeters equal 1 inch. Then we'd modify our conversion a bit. We'd add 100 centimeters over 1 meter. As we move to our knowledge of 1 inch equals 2.54 centimeters, continuing, 1 inch divided by 2.54 centimeters times 1 foot over 12 inches, and using our calculator, we get 91 feet per second. So the distance traveled in feet is 91 feet per second times 0.70 seconds equals 63.8 feet. Or we could have just converted 19.5 meters, our original distance traveled, to feet. See how the conversion factors clear unwanted units? They nicely cancel. So you know whether to multiply or divide with your calculator. Units guide the process. And we see that we get the same answer, 63.8 feet. That's yum. I want to leave you with a question. If Fast Frida closed her eyes for twice as long as 7/100 of a second, how much farther in distance would she travel at the same 100 kilometer per hour speed? Maybe you could use an equation to guide your thinking. Until next time, good energy.
All right. So I think we're gonna acceleration and we're getting ready to wrap up.
These videos all in the book, right?
Yes, sir.
So acceleration means there must be a change. And I can put this in shorthand notation. Like that, and I can give you a numerical example. Let's suppose you're buying a car. And someone says, hey, this car is really, really neat. Doesn't look very nice, kind of a little bit tacky, but this thing will accelerate. This car will go from 0 to 60. What's the person telling? 0 to 60 miles an hour. Does that say anything? Then you buy the car and you find out it takes you half an hour to get to 60 miles an hour. Okay. So when you talk about acceleration, you talk about how long does it take to do that? Well, let me give you an example. If I have a car that'll go from 0 to 60 miles an hour in 10 seconds, what's the acceleration? Try it. Let me help you. the car is going to change its velocity by how much? From 0 to 60 miles an hour, okay? So there's going to be a change in velocity of 60 miles an hour, right? Did I tell you how long it would take to do that? 10 seconds? So I'll divide that by 10 seconds. S per second? So you know what the acceleration of my car is? Anyone have a calculator? Maybe you can do it in your head, okay? You can, okay? It's going to be 6 miles per hour per second. So the acceleration of that car is 6 miles per hour per second. And if that acceleration stays uniform, stays constant, that's to say then, so long as it's doing that, every second goes by, the car is going to be going faster than the second before. By how much? By 6 miles per hour. It'll gain 6 miles per hour every second. Ain't that neat?
Right? It's like if we throw the ball in the air with an initial speed of 40 meters per second, right? It stays in the air, right? 4 seconds, right? Then that means it stops, right? And it loses what? Every second it loses what?
Speed.
Well, how much?
10.
10 meters per second. That's how much the speed is changing per second. Okay? That's the same thing. Let's see. Let's look at this one.
Let's discuss free fall. When air resistance doesn't affect the motion of a falling object, when the only force acting on the object is that due to gravity, we say the object is in free fall. Here we have a boulder, heavy enough that air resistance is negligible for short falls. Phil Physiker drops the boulder over the edge of a tall cliff. Since only gravity is significant, the boulder experiences free fall. We'll only discuss free fall here. The falling boulder picks up speed as it falls. This pickup is acceleration. Acceleration equals the time rate of change of velocity, given by the equation A is delta V per delta T. For straight line motion, we can use the terms velocity or speed interchangeably. Recall that speed is the magnitude of velocity. In free fall, during each second of fall, the exact same pickup of speed occurs. We say the boulder falls with constant acceleration. Here's Phil at the top of a cliff, ready to drop the boulder over the edge. He drops it, and it accelerates downward. Wouldn't it be nice if a speedometer were attached to Phil's boulder so that we could watch the gain in speed as the boulder falls? We wouldn't be able to see the readings, so we blow up the speedometer for better viewing. We start from rest, so the speedometer reading begins at 0. This is our initial speed. Our speedometer also has an odometer that measures distance traveled. Its reading is set to 0 at the time equals 0 mark. Phil releases the boulder
So
with
this
a
is what's on your
speedometer,
dashboard,
and 1
right?
second later, the boulder is gained 10 meters per second during this 1 second interval. The odometer reading is 5 meters. That's 5 meters, not 10 meters, as we'll explain later. For now, just concentrate on changes in speed. 1 second later, the boulder again gains 10 meters per second, and the speedometer reading is 20 meters per second. And our odometer reading is 20 meters. 1 second later, the boulder again gains 10 meters per second, and the speedometer reading is 30 meters per second. And our odometer reading is 45 meters. And another second later, another gain of 10 meters per second finds the speedometer reading 40 meters per second. At the 4 second mark, we find our boulder has fallen 80 meters at the instant its speed is, as said, 40 meters per second. Let's make sense of these readings. First, the acceleration. We see that acceleration equals delta v per delta t equals 10 meters per second per 1 second equals 10 meters per 1 second multiplied by second, which equals 10 meters per second squared. Notice how the symbol for second appears twice. First, the time and velocity, and second, the time during which velocity changes. That's why the second squared. How do we know that the acceleration of free fall is 10 meters per second squared? Because we've measured it time and time again. You can do the same with actual measurements in the lab, where you'll get 9.8 meters per second squared. To simplify calculations, we round this off to 10 meters per second squared. We call the acceleration of free fall g. That's g for gravity. From g equals delta v per delta t, we can say that delta v equals g delta t. Or simply, v equals gt, which reads, the speed gained in an interval of time t is equal to the acceleration times that time t. Since g equals 10 meters per second squared, we can write speed gained as v equals 10 meters per second squared times t. Notice how this equation accounts for the white speed readings. At 1 second, v equals 10 meters per second squared times 1 second equals 10 meters per second. At 2 seconds, v equals 10 meters per second squared times 2 seconds equals 20 meters per second. At 3 seconds, v equals 10 meters per second squared times 3 seconds equals 30 meters per second. At 4 seconds, v equals 10 meters per second squared times 4 seconds equals 40 meters per second. How about distance fallen? Here's where equations guide our thinking. From the equation for average speed, we know that distance traveled equals average speed multiplied by time. That is, d equals average speed times time, where average speed is v sub 0, our initial speed, plus v sub f, the final speed, divided by 2, multiplied by t. And we see our initial speed in this case is 0, and v sub f is the
All right. I think that's about it for the day. So Monday, 11 o'clock. Be ready. Have a good weekend.